Let's look at components of a hypothesis test. As mentioned before, the good news is that you're already familiar with how to do a hypothesis calculation if it involves a sampling distribution of the sample proportion, which is the situation we'll demonstrate, the concept of a hypothesis test. However, the language, the vocabulary that describes the previous components is about to change, and you need to remember this vocabulary, that is the language associated with hypothesis test. So we changed the words to let the reader know that what we're discussing now is a hypothesis test. Let's look at an example, because the statistic we're going to use is p-hat, right? So we see our old known p-hat. This process will be known as single proportion z-test. Summaries created from data that are restated as a unitless value typically associated with a variation of the statistic. The z-score, the number of standard deviation, is a prime example. These restated summaries will be called test statistics. So what we'll be using z-scores, for example, what are other test statistics? There is a T, student T. That we're not using at the moment. The chi-square is another one. So there's many different ones that each one is used for a particular situation. So what is this? The test statistic we're going to use, again, is known as single proportion z-test. And this is the value. So this is the formula, which is the same one you used before. And again, so this is known as single proportion z-test. And again, this is the same formula as before. And you'll sometimes see, if you look at a book, that this little p will get a little zero here. What appears to be a zero, but that's just p. It's called p naught. The little zero is mentioned p naught. And that's just say that, hey, look, this is just a placeholder for an actual value that's connected with a null hypothesis. Another thing we want to remind ourselves is called the effect size. The logic of a hypothesis is critical. The numerator of the test statistic, this right here, reflects the difference between what I expect and what I got. So what I expect is sitting right here is this value. So what I expect is described using this population proportion, and what I got is described by p-hat. And this difference is called the effect size. This is not the only way to do effect size, and there's different types out there. Right now, we're going to keep this very simple. And we're going to say, look, the absolute value of that difference is the effect size. And all it is measuring is how far these two are away from each other. Please note there's the only one definition of effect size. It is a loose idea that attempts to reflect what we're observing outside of statistics. So this is not about statistics. This is saying, well, how big was the difference between the two? Because this measurement is typically used in the description of a situation, part or some paragraph. It is just quoted as a positive value. Statistics cares about the rarity of the event, but for practical, we'll be interested in the actual difference. And we'll look at this later. Lastly, we look at this thing called the p-value. When we're calculating probabilities, when we are studying sampling distributions, we did not have a purpose with respect to the calculated probability. This is now going to change. The calculated probabilities are now called p-values. Below is the meaning of the p-value. You must remember and understand this definition. Now, what is the meaning of a p-value? The p-value is the probability of observing a statistic as extreme or more extreme than the one from our sample, given that the null hypothesis is correct. And I cannot emphasize this enough. We're going to assume the null hypothesis is correct, and that is signified by using p right here. So this is your null value. It gets this position because we assume it is true. And now what we're saying is What's the probability of observing statistics extreme or more extreme from the one that we got, given the null path is correct? So that's what this difference right here. How extreme is this difference? That's what it's asking. What's the chance of observing something that far away? Note the probability is based on the sampling distribution of our sampling process, whatever it happens to be. So in this case, it is the sampling distribution of proportions. The p-value corresponds to the probability of a range of values, of which your observed value is the beginning of that range. It is not about that single value. So this value that we get, this p hat, the probability is not about that value, but it is about the cutoff using that value. The p-value is used as evidence against the null hypothesis. The evidence comes in the form of how likely it is to see this result if the null hypothesis is correct. So now let me draw some pictures to make all this more clear. Suppose I have my null hypothesis here. And then again, I'm going to use this little knot to get just emphasize that this is the population, but there's an actual number. This is the symbol representing the population proportion. And let's say that I'm looking for less than. And again, this signifies that we're actually using a data value. To do these calculations, our sample size has to be large enough. So again, we'll meet our criteria that n times p must be greater than 10, n times 1 minus p must be greater than 10. So here's p naught. And there is where p hat lies. So notice p hat's not sitting anywhere in this description. Once we get our p hat, it lies somewhere. Could it lie in this side? Sure. But now, because I'm looking for less than, when it becomes directional like this, you have to go in the direction that this thing states. I'm looking at less than. So what is my p-value? The chance of observing this value or something more extreme. P-value is the probability of observing a statistic as extreme or more extreme than the one from the sample collected. So in this case, we got this far away. That's my effect size. But we're trying to figure out, well, what's the chance of that, just that effect size or something more extreme? So the p-value is this right here. What if it landed, I'm gonna draw another picture. What if it had been this? And where is p hat land? Let's say p hat landed right here. Same, so notice the direction is based on this. So I'm still lumping these whole things together. Where is the picture of the p-value? Well, because this is less than, I have to go less than, I got in this direction. So the p-value is this. I have to go through the parameter and keep going to the other side. So you can see here the p-value is actually bigger than half. One thing that we note, if we see this, do we really need to calculate the p-value? Probably not. So again, the p-value becomes this. Because notice, we were hoping that the actual value of the population proportion was less than what was quoted, but our p-hat value didn't provide any evidence. As a matter of fact, not only did we not get something that was less than it, we got something that was greater than this value. So we failed in a direction. Here, at least is on the correct side. It is actually, p-hat is up to the left. The question becomes, is it far enough away to the left? If this is greater than, then everything reverses on the other side. What about not equal to? If we have not equal to, again, the null is going to be the same, so I'm only going to describe the alternative. What if it had been this? Now we have no direction. And because we have no direction, then we must move away from this. So here's where it landed. So to move away from this, I have to go in this direction. But this value will not be the p-value. Instead, what we're gonna do is we will calculate this. So this is some, call this, I don't know, some probability. I guess like this P prop, just not to confuse, there's too many P's running around. And in that case, what is the p-value? Well, what we're going to calculate, because this is directionally, we're going to ask the question, what's the chance of getting this far away on either side of the mean or even further away? So even though that's where we landed, we'll have another one on the other side that is a kind of a ghost. The same distance, the same effect size. So whatever the effect size here, it's the same here. And again, remember what the effect size is, the difference between these two values. And then we'll go extreme on the other side as well. So the reality, this is totally symmetric. So really the p-value in this case is not this, it's not this. The p-value will be twice this right here. In other words, the sum of these two is the p-value, but it's just easier to calculate this probability and then double it. And that becomes the p-value, which is a chance of seeing a statistics as extreme or more extreme from the one that we collected, given the null hypothesis correct, but in this case, it's on either side. So you'll notice that when we do a two-sided, the p-value will be actually bigger, twice as big as the one with only one direction. And how does this help us? Or what is this saying? Well, I'm going to draw one more picture. Let's say that I'm looking at this. Let me just change the direction for a moment. How does this help us? Well, what's going on here? So I'm going to draw two pictures. There's a parameter. Let's say, assume parameter, that p hat lands right there. And just for argument's sake, let's make this nice and clean. That value, there's that p-value, which is this area. Again, notice I'm going to the right. So when I land, I need to go to the right. Had I landed here, I would still go to the right because this has direction. So this becomes my p-value. Now, a 3% p-value, we're going to find out, really could be enough evidence to suggest this is not correct. In other words, if it's 3%, only if this number or something more extreme only occurs 3% of the time, then this may be enough evidence to suggest that this is not correct. How does that work? Because the belief is this. I'm going to draw another picture. So in fact, I'm going to try and make it underneath. So here's where this one lies. This is the same location, so I'm going to try and draw them so that everything nicely lines up. But what's not going to line up is the actual mean. Maybe what's happening is the reason we got such a rare value is because this is not correct. And indeed, just like what this suggests, the real population proportion is something bigger than the one we believed is to be true. And when we do that, when I draw my picture now, it's normal distribution. I'm trying to make this the center of it, a little off. That's not very good. Hope you get the idea. Do that. Right. So this is some other, I'm going to call alternative, which I don't know what it is. But in our minds, we might think, hey, the reason we got such a rare thing is because this is not correct. It's really here. And now that explains this value. It wasn't that this thing was really rare when this is true. It's that this is not true and this is correct. And what I got is something that is pretty common. Let's say that this turns out to be 20% of the time. So if it was 20% of the time, that would be very common. And this is the reality. So, but of course, we never know what this value is under this whole process. All that this will say is, hey, we found something and it's rare. So now we're questioning this value as to the truthfulness of this.